For today's session, we have Juan Margalef, and he's talking about symplectic formulation of the covariant phase space with boundaries. The floor is yours.
Thank you so much. Thank you, everyone. I'm very, very happy to be here finally. I was there for some 6 months, and Eva was the best boss I've ever had by far. So I'm very excited to be back, even if it's virtual. Hopefully, it will be in person soon, but the time will tell. So yeah, I thought that this talk for the audience that is very symplectic audience, this would be the kind of things that you might be interested in. That's also the thing that I've been interested in the last few couple of years. Although my approach is more physical, I work between the mathematics and the physical world, but I try always to apply to a physics theory or a physics approach. But still, the beginning before applying to physics, I think is quite interesting even for mathematicians. But keep in mind that the goal is to apply to some physics. I will say maybe if I have time at the end, some things about what I've done. But I wanted to talk about the symplectic formulation of the covariant phase space, and in the case of boundaries. So I will explain what is the covariant phase space, and for that, I thought that the best thing would be to work with one complete example, a very easy one that is called the scalar field. So you just take this F will denote the space of fields, and our fields are just functions on M that you can think are, for instance, the wave equation that is going to have. So you have some field, you can think the temperature or the some sort of thing that in the end will be the wave equation that will spread across the universe, and this is the Lagrangian. The Lagrangian, this is not the kinetic part. You can think that this is the covariant derivative of the phi. I use indices, but this is just like, you can think as the velocity kind of thing. So this is like the velocity square. So this would be a generalization of a kinetic term. So the mass is one half of the velocity square. And then you have to put some volume. Here is some background metric, it speaks. You can think just the Minkowski, the Euclidean with a -1. And this is an end form. This is a top form. And then this is very standard in what is called the variational calculus to take the variation of this Lagrangian. In the physics notation, this is called with a delta. In the mathematical notation, is called with sometimes called the vertical derivative, and sometimes it's with this double D. I like this double D, but it's just taking variation. It's just like linearization of this Lagrangian. So you take the linearization with respect to phi. So this 1/2 will go away because this is symmetric. So you will get this. And now the standard theory of variational calculus tells you that you have to integrate by parts if you have an integral, or use the Leibniz rule to remove the derivatives in front of the variation. So you want this partial derivative or this covariant derivative to be outside. And the way to do that is just by Leibniz rule. Well, this is the Levi-Civita connection, so the volume does not play any role. So you get something like this. I'm just doing Leibniz rule. So the derivative of the first one gives you this, and the derivative of the second one gives you this. So that's why there is a minus. And the volume is 0, the covariant derivative of the volume. So that's great because this term, if you notice, this is a divergence. And when you get the divergence as the volume, this is actually a Lie derivative. And if it's a Lie derivative, it's actually an exact form. So Lie derivative of the top form is an exact form. So you can write this expression something like this. The equations of motion times d phi. So the equations of motion is going to be this. The square is what is called the D'Alembertian. So it's going to be this, or the Laplacian kind of thing. So it's this term times the variation plus something that is exact. And as I mentioned, a divergence is a Lie derivative. A Lie derivative is something that is exact by the Cartan's magic formula when you have top forms. Usually you have di plus id, so the Cartan's magic formula. But for top forms, if you take the derivative, exterior derivative of something, an n form is going to be an n+1. This is 0. So you only get the exact term. So you get something like this, and this v is actually this term. This vector is here. So great, we have this, and now how do we get something that is symplectic? Well, we just take the exterior derivative of this. This is one form. You can see that there is one exterior derivative, so we can take the second exterior derivative, or what sometimes it's called the second variation, but it's a bit misleading. So we just take the exterior derivative of this, and then we get the variation of this, and then I put this double wedge because it's just to remind that this is with this double, but it's just like the normal wedge. Well, not the normal wedge, is that the wedge over this space of fields. I will mention something later about that. But if you notice, this is actually the position, kind of, and this is kind of the momenta. So actually we have here the Darboux theorem kind of stuff. So it's dq wedge dp. Of course, I will go into more details later, but keep in mind this example. So we get some Lagrangian that is like this. We take the variations, we do the Leibniz rule to remove the derivatives of the variation, and we can always, we'll see that we can always do that. In particular examples, for sure, we can always do that, and it's actually a theorem. So we get some of these that is called the equations of motion, which is the wave equation, as I mentioned before, and then we get some that is called symplectic current and the symplectic form. You integrate, you take the exterior derivative. So that's why, or that's how the symplectic theory or symplectic geometry appears in these fields, in this field of physics that is called field theory. Obviously, you can prove that this is a symplectic form. It's obviously closed because if you take the exterior derivative of this omega, there is a d square and this is 0. And you can prove that is non-degenerate because essentially this is dq dp. And if this is dq dp, this is non-degenerate. But it's only over the space of solutions, because there is one choice that I will mention later that is only true if you go to the space of solutions. If you are in the whole F, it is still a symplectic form, but there are more choices to do. Perfect. If there is any question at some point, just ask me. You can interrupt me at any point. Great. So now we have that. Keeping that example in mind, let's go to what I call a crash course on differential geometry. When I say crash, it's very, very crash. So we're going to just mention the space-time. We have M is a space-time that is finite dimensional manifold. Usually it's 4-dimensional, but here it can be n-dimensional. Usually you have the tangent bundle, and you can have some vectors, and this is how I denote the vector fields. You can have the cotangent bundle, you have the one forms over M, and you have in general higher order tensors, R times, this is this is contravariant and this is covariant, I think, or the opposite, I never know. So you can get tensor fields. But now we have also the space of fields, which is an infinite dimensional manifold. Is usually taken at the space of sections of a tangent bundle, it doesn't need to be a tangent bundle, of a bundle. So for instance, you can have metrics. The metrics are the sections of a certain bundle. The velocities, if you're working with fluids, for instance, you have vector fields. So this is the sections of a tangent bundle, and so on and so forth. You can have a lot of fields. You can have very weird, complicated spinorial fields. So, but they are all in general sections of some tangent of some bundle. So here F is an infinite dimensional manifold, but still we can give some sense of what it means to be the tangent of this space of fields, and we can define vectors over F that I'm going to denote with this double. Double stroke means always that belongs or is related to F. We can also define the cotangent bundle of this F. We can define one-form fields, and in general, we can define higher order fields. We have to be careful with some of the theorems that we think that they are true, because in infinite dimensional manifolds, they might not be true. For instance, we can have some troubles with the flows and so on. But in general, we can still define, here we have the exterior derivative, interior derivative, and lead derivative, and we can define the same in this infinite dimensional manifold that is F. As I was saying, the lead derivative, you have to be a bit careful, because some things are not exactly as true or as nice as in the finite dimensional case, but still we have the differential calculus that we know. We have the Cartan's magic formula. We have that the L and the D commute over forms. We have that these commute the commute errors between the D and the Lie derivative and the interior product. You all have that. You also have the Lie bracket and so forth. And so much. All these things you have it. Now, just to mention, there is this is like the physical perspective, but of course you can still give like the mathematical background is given by what is called the infinite jet manifold or infinite jet bundle, sorry, that I guess all of you have heard about it. I don't know how familiar you are, but still you can properly define everything within the infinite jet bundle. And there is actually some sort of, it's called like a projection that takes you from the infinite jet bundle to this F. So the infinite jet bundle is a bit more general, but for the physical perspective, you're not interested in the whole infinite jet bundle. You're only interested in this F, because in the infinite jet bundle, you can have some sort of global things, like a field that depends on points that are far away, like in the whole space-time. And that's physically that doesn't make sense. You want everything to be local. And well, this is what is called, when you merge this space-time with the fields, you get what is called the bicomplex framework. So things will depend on points and things will depend on fields. So before I define this Lagrangian, that depends only on fields, but actually I could put some explicit dependence on the point. So I want things to depend on both things. This is what is called bicomplex framework. It's very well known. Anderson has a very nice book about the bicomplex formalism, and it's pretty neat.
So I think we lost Juan's voice.
Yeah.
Sorry, Juan, we cannot hear you now. We just lost your voice, but we still see you.
We lost you just here in the part 3.
Yeah, here.
Can you hear me?
See.
Hello?
Yes, now it's working.
No?
Yeah, it's working. It's possible that.
Can you hear me or not?
Yes, maybe you can't hear us.
Hello? Okay, nice. Good. So yeah, I was saying that I'm gonna explain what is the CPS, the covariant phase space, and I'm gonna compare what I call the CAN, which is the canonical formalism called by the physicists, which is a bit misleading because it's not exactly canonical, but we'll see what I mean by that. So the canonical formalism is just when you take your space-time and you break things into, you assume that your manifold is what is called globally hyperbolic, which essentially means that is of this form, R times sigma, where sigma is n minus one dimensional manifold. The thing is, like, this breaking is not canonical. You can break in many ways because this is just is diffeomorphic to this. So you have to fix a diffeomorphism to break into space and time. But this is the canonical formalism. You take every object that you have and you break it in something tangential and something perpendicular. Meanwhile, the covariant phase space deals with the fields over the whole space-time. So you don't break anything. Now, the advantages of these canonical formalisms is that you gain a dynamical perspective. So you can, in particular, do numerical approach because you get something that is like your instant of time, and then you can put some initial data, and then you can evolve this initial data to get some dynamics. So t equals 0, you get this, at t equals 1, you get this, at t equals 2, you get this, and so on. You also get some universal structures because these will live in the tangent bundle or the cotangent bundle. And from the cotangent bundle, you have the canonical symplectic structure, and that is why it's called canonical. So you get this universal structure is very useful, as you will know. You get all the Hamiltonian, Lagrangian formalism that you can use. And it's also very useful for quantization schemes because the symplectic formalism is very useful in physics because it's like the first step towards a quantization. Which quantization? What is called well, one that you can get is the canonical quantization, that is called in physics. It's just when you get the Hilbert space, and then you promote all the operators like the Hamiltonian to quantization. It's like a very physical thing. It's not very well defined mathematically, and I'm not gonna get into that. I don't do quantum stuff, but it's what is called the canonical quantization. Yes, exactly. The cotangent band. Yeah. So that's when I say quantization schemes, I mean like this is the first step in most of the quantization schemes. For instance, the one that Eva is mentioning. I don't know if that appears in the video that Eva is talking. I hope that it doesn't look like it. But Eva was asking about the cotangent band quantization. So yeah, that's one of those that a lot of them you need the symplectic structure, and sometimes you have problem because it's only a pre-symplectic structure, so you have to reduce. Blah, blah, blah. So yeah, that's why it's important. However, there is some what is called, or we can think of, there is an apparent loss of symmetries. You may have some symmetries that are of the whole space-time, that when you break between space and time, there are some symmetries that disappear. Of course, the symmetries are there because the theory is invariant under certain symmetries, like for instance, diffeomorphism. You can have a theory that is invariant under diffeomorphism, but if you break, then suddenly it's not, because obviously you're breaking. However, in the end, you should be able to recover these invariants, but only at the end. So you cannot use them in between. So there is this loss of symmetries that you somehow you don't have them, so you're not able to use them. However, the covariant space has explicitly the symmetries because you're working with the whole space-time. Like at the beginning of the example, I didn't break anything. I had the field, the scalar field defined over the whole space-time, and I didn't need to break absolutely anything. It's also very useful to study what is called the null infinity. So whenever you have space-time, you can compactify the space-time in such a way that there is what is called the null infinity. Is where the radiation arrives. So for instance, if you ever heard about the gravitational waves that they can measure here on Earth, there are some detectors that you can get where are the gravitational waves that arrive on Earth. The way to model that mathematically is to study what is called the null infinity, which is take your space-time, compactify, and at the band, you had a boundary that represents the infinity, and one part of this boundary is what is called the null infinity. And all the radiation that arrives to the null infinity is the radiation that you will get on Earth. That you can compare and you can try to do some predictions and then compare it on the detectors here on Earth. You also have some what is called conserved quantities. It's very useful to study what is called these conserved quantities. For instance, when you get a black hole, you can define what is the mass of the black hole. It's not easy to define what is the mass of the black hole. You really have to go to null infinity to define it. It's a very intricate definition, but within the covariant phase space, it's not that hard to define some quantities that they are conserved in a way that I'm not gonna get into. And another thing is like the higher derivative theories are actually the same as the first order theories, because the first or higher orders is when you get a 3+1 or a decomposition. It's when it lives in the tangent or the cotangent, or you have to go to higher order theories. It's like, oh, I need velocities and position, then you're on the tangent bundle, or position and momenta, and then you're on the cotangent. But maybe your theory also requires like higher orders, like 3 or 4 derivatives, so you need more initial data. You need the position, the momenta, the acceleration, or whatever it is. You have to go to certain cotangent bundle. But however, in the covariant phase space, there is no such a thing. It's like you don't care, it's just the space of fields, and the space of fields is the same. It doesn't matter if your Lagrangian has more orders or less orders. You don't care about that. So they are on equal footing. The drawback is that there is no canonical structure. We don't have this universal structure because we're not working on a cotangent bundle. Well, we have those two perspectives, and what I'm going to show is how we can actually build a symplectic structure in both of them, and they actually turn out to be equivalent. That's something that we have proved recently in full generality. So the covariant phase space formalism in a nutshell. So imagine, well, we have the action that I didn't introduce before the action. I only introduced the Lagrangian, but the action is just an integral of this Lagrangian. So usually it's like you get a field, you evaluate, here is not, it doesn't have to be a scalar field. I put the same letter, but maybe it was not a good idea. This is just any field, and actually it can be several fields. It can be metrics, vectors fields, 1-4 fields, 3-4 fields, whatever you can think of. And here they are all gathered in this F. And this object is called what is called the action. It's just the integral of this Lagrangian. The Lagrangian, recall, is a top form. However, it's customary to remove this dependence of phi and just write something like this. So now the Lagrangian is something because, well, I didn't mention, but on the complex formalism, you have M times F. And whenever you have a product of two manifolds, everything is bigraded. You can think if this is M and this is M2 and one of M2, you can just think that here you have X coordinates, here you have Y coordinates, and then you can have a form that is dx wedge dy. So you have one X and one Y, but you can have dx1 wedge dx2. So you have 2 in here and 0 Ys. So you can always bigrade the things. So the grade here means that it's an N form on M, a 0 form over F. Now, if you have two Lagrangians that they are equal up to some exact form, so obviously they define the same action. That's why the Stokes theorem, because we don't have boundary at this point. We will add it later. So when you plug this L prime in here, you will get the integral of dy. The integral of dy is 0. Now, is the converse true? It's not. Funny enough, you need to go to what is called contractible bundles. You can have something, actually, the action that is 0, however, comes from a Lagrangian that is not exact. And that might seem weird because if you know something about the Stokes theorem, the Stokes theorem is actually, it tells you that whenever you integrate something that is exact, it gives you 0, but it's actually you have the converse. Whenever you integrate something that gives you 0, is exact. So that seems to contradict this, but it does not, because remember that you have this. You have to evaluate, and then you will see that this is exact. So for every phi, this L phi would be exact. But when you remove the dependence, what you get is something that it might not be continuous, for instance. The potential that you get, this Y, will depend on phi in a way that is very problematic. So you change the phi maybe slightly in a topology that you are chosen, and then this Y will completely change. So in general, you don't have that. It's like there is no global potential Y that this is true, unless you get some contractible bundle. Well, this is a sufficient condition. So if you get contractible bundles, this problem, essentially you're trivializing the cohomology in this vertical direction in these fields. So this problem of this globally, that is not globally defined, it does not appear, and then you get this. And in physics, a lot of them are contractible, not all of them, but a lot of them. So this is good enough. Now, we can define what is called the spatial solutions are the singular points of these actions. Now, when we compute the singular points of these actions, what we are doing is we're taking the exterior derivative of this S. Under reasonable conditions, they will commute with the integral, and you will get the exterior derivative of the L in the fields. Now, this is a theorem that you can prove. There are certain conditions, certain hypotheses, but for our purposes, we can assume that this is always true. Because even when it's not true, you have the only problem is that you may not have unicity here in theta. But in general, this is true. In practical examples, we just do what with the example that I did at the beginning. You just remove the covariant derivatives from the variations and you just put it elsewhere. So you can always do that. And when you plug this into this d theta will disappear. There is the Stokes theorem will remove that, and you will get that this is equal 0 if and only if actually the E is equal 0. So you get the equations of motions and what I call the Euler-Lagrange equations. So the spatial solution that is given as the singular points is actually the same as this one. And I will denote with this double J just the inclusion over the whole space of fields. And now, what we're going to do is, first, what happens if we change and we take another representative? if you take another representative, because this is our physical object is the action, but we can have different Lagrangians. So if we get another Lagrangian, they are going to be equal up to exact form because we're assuming these contractible bundles. I didn't say that, but even if it's not contractible bundles, then here what you get is some cohomological classes that they are very easy to handle. So even when this is not true, this will be true up to, you might have to add some cohomological classes, but they will disappear. So they don't play any role. So here, if you take another L prime, when you do that, you will get actually the same equations of motions because this is actually like a unique decomposition. So when you plug this y will actually join with this theta. So what you get is something like this, theta plus dy. But now again, we have to extract this symplectic potential. So actually we'll get something that they are equal up to some closed form. But now there is a very nice theorem that tells you that actually every closed form is actually exact when this degree is higher than 1. So in the fields, the cohomology is trivial, except for the 0. So here you get something that is has degree 1, if you notice, because here this has degree 1 in the fields. So this has to have degree 1 in the fields. So when you extract the potential, you are extracting up to some exact form. So this is the ambiguity. When you define the theta, this is the most general theta that you can define. So imagine that we are both, we're given an action and each of one are deciding which Lagrangian we take and which theta we take. When we compare our results, they will be all of them equal up to these exact things. Exact in the vertical direction and exact in the horizontal, exact in M and exact in E. And no matter what we do, they are always going to be like that. So now what we can do is, well, we just take the exterior derivative of that, and we're going to take some Cauchy embedding. That's the part that I didn't mention at the beginning. We take a Cauchy embedding, we take something that is a Cauchy surface that there always exists because we're assuming that this is globally hyperbolic. And we just take that, we take the exterior derivative of this theta. Remember, the theta is an n-1, 1. And now when we take the exterior derivatives, an n-1, 2. n-1 on M, a 2 on F. But if we take the pullback to sigma, this will be an n-1, 2 over sigma times F. And then when we evaluate, again, I'm going here, we have to evaluate, but we always assume that they are evaluated, or we just assume that they can be evaluated at the end. So here, when we integrate, this is a top form on sigma. So it makes sense. Now, what happened? Each of you has different theta. What happens with your theta? Are they going to be the same or not? So when we compare, it's like, oh, I get this theta prime or this omega prime that is defined with this theta prime. But now remember that this theta prime and my theta, they are equal up to these exact things. Now, this d squared, this is an exterior derivative, so d squared is going to be 0. So the y dependence disappears. Now, this dc, you can prove that these horizontal exterior derivatives, so the exterior derivative of M and the exterior derivative of F, they commute or anti-commute. It depends on some choices that you have to make when you are defining things, but either commute or anti-commute. The important thing is that this d can go in front, and by the Stokes theorem, this will disappear as well, because we don't have boundary. That is very important. So if you don't have boundary, no matter what we do, if we are given the same action, we're all going to end up with the same symplectic form. So with this recipe, we have a canonically, a symplectic form canonically associated with the action. And all of us will agree on that. What is the problem? If you have boundary, this term will appear, and actually it could be whatever we want, because this z is absolutely arbitrary. It's a choice that you can make, and you can add absolutely everything you want. So when you integrate by parts, or when you use a Stokes theorem, it will get a boundary integral that can be absolutely anything. And that was the problem when I started to study that. It's like, oh, then you have to do some choices based on your physical problems. And then what people would say is like, oh, I need this result, or I need this behavior, so I make this choice. And that's how people were solving that. And when I read that, I felt that was very wrong. So it's like, there should be some way to do that. And then at the end, I will explain how you can solve the problem of having boundaries and still be cohomological. because this notice that this is cohomological. It does not depend on the representative. Here, you can think that this is the cohomology on F and this is the cohomology on M. It does not depend on any of the cohomologies. However, it does depend on the embedding. Here, when making a choice in the embedding, and if you choose another embedding, it would be different. However, if we go to the space of solution, remember this is the inclusion of the space of solutions in the space of fields. This is actually a true symplectic form, and it does not depend on it. It does not depend on the embedding. The thing is, like what you're gonna see, that there will be an integral that depends only on E, and E are the equations of motions, and the equations of motions are 0 over the space of solutions. So essentially, if you choose this and I choose this, we can just use Stokes' theorem to convert this integral over these boundaries of something, an integral in between. And this in between will depend on the equations of motions. I don't have time to show you the proof, but it's not very hard to prove that. So we're good. We're happy, everyone. It's a very canonical way of building a symplectic form once you are given the action, and also to define this space of solutions. Now, what happens with the Kant formalism? This what is called canonical, but I think it's very misleading because it's not canonical, as we will see. So imagine you have your fields, and we have break every field into the tangential part and the normal part. If you have the metric, you can think you're doing the tangential metric, and then you have the perpendicular thing. So you have to break all the components, or each of the indices if you want. So if you have a vector field, you can break it always in the normal direction and the perpendicular direction. And if you have a metric, it's like you have to do that for 2 vectors. So you have what is called the lapse, the sieve, blah, blah, blah. It doesn't matter. You just break everything into normal direction and the perpendicular direction. You might have used the Gauss-Kodachi equations and some of these theorems of differential geometry, but you can always do that. So now you end up with a bunch of fields. It might be a lot more fields than you begin with, but it doesn't matter. It's just a lot of fields. And they are what is called the configuration space over sigma. Now we forget about N, we forget about a space-time. We're only thinking about a picture, like an instant frozen time. So we are, okay, this is our initial condition, this is our configuration space. And usually we're gonna take the tangent to that. We're gonna assume, so for this talk, that the theory is first order theory, but we're gonna explain it's actually true for any order. But let's assume it's first order, and then we're gonna define what I call the Kant-Lagrangian action. I call it, it's not an action and it's not a Lagrangian, but people sometimes call Lagrangian, people sometimes call action. It's something in between, so I decided I'm gonna call it both. Why not? So the thing is, like, I'm gonna take a Lagrangian that lives on sigma and depends on the fields and the position and the velocities. So it's an n-1 because it's a sigma and a 0 in the fields. And I'm gonna integrate on sigma. And that is usually what is called the Lagrangian action, and this gives you a number. However, we have the time. So actually, the action is gonna be the integral of this, but taken over curves. What we're gonna do is, like, I'm gonna feed a curve, and I'm gonna take the position, and I'm gonna take the velocity. And I'm gonna integrate on time. This is the classical mechanics. If you, instead of, if there are no fields, this is classical mechanics. And if you get fields, this is just the Lagrangian or Hamiltonian formalism if you have ever studied that. So I'm not doing anything crazy here. However, we can still prove, the proof that we used before is actually true here. When you take the exterior derivative of L, because this is a top form on sigma, you have this decomposition. Now we have more fields. The fields are actually positions, are actually velocities. Here, there are some locality that you, like some trivialization that you have to assume. Otherwise, you have to work on a locally on the fields, but it's not a big problem actually. So before, remember, we had the equations of motions times the variation of the fields, and now we just have fields. I call it A10 and AI0 and AI1 because when you're working with higher order theories, you will get more terms like A2, A3, A4, up to the order of theory. And then you get something that is exact, and I put this hat to make it different from the previous theta, because now we're working with sigma. So when you plug, you take the variation of this action and you plug this, notice that now the velocities are not independent variables. The velocities are actually the derivatives of the other fields. So you can integrate by parts, and what you get is this, which is actually the Euler-Lagrange equations. If you remember from the course of mechanics, is the variation, the time derivative of the variation of the Lagrangian with respect to the v's, which are these, minus the partial derivative of the Lagrangian with respect to q, which is this. Okay, if you remember well, if not, it's not important. You just get this, and this equal to 0 gives you, but now they are dynamical. Before, remember, there is no time, so they were just PDEs that you get no meaning to the coordinate. If you take some coordinates, they might have no meaning. But here there is one coordinate that has always meaning, and it's the time. So here we have a dynamical perspective that we can evolve and go from layer to layer to build our whole solution. So now, we know that in the cotangent bundle, we always have this symplectic form. So we have the position, we have the momenta, and we can always define this. I wrote it like that. There is, it's a bit abuse of notation because here there is some pairing that I'm not putting like between position and momenta, but for our purposes, it's good enough. So that it resembles something that you might be familiar in finite dimension. Another way, because here we're in the tangent bundle, and the way to go from the tangent bundle to the cotangent bundle is through what is called the fiber derivative. The fiber derivative in classical mechanics is partial L with respect to the velocity. You take the momenta are defined as the derivative with respect to the velocity. In infinite dimensional things, you have to be more careful, but it's exactly the same. You're taking the variation or the partial derivative with respect to the velocities. Okay, here is just you take some direction v and you take the, that's why it's called fiber derivative, because you have your manifold and you have your fibers, which are the velocities, and then you take the derivative only in that direction. You don't move the point. So you get these, this position, these are how you define the momenta. However, these might not be, if this is a diffeomorphism, they are good. The Lagrangian and the Hamiltonian formalism is the same. But it might not be injective or it might not be subjective. So actually, in general, it's not subjective, and you get what is called the primary constraint submanifold. You get that not all momenta are attainable. You cannot reach all possible momenta. So instead of working in this whole cotangent bundle, you have to work on the image of this fiber derivative. And actually, this is the symplectic form that we are interested in, is the one that is induced from here to here. And that's why I think it's very misleading to call it canonical, because this is not canonical. This one is canonical, but when you do the pullback, it's not canonical anymore. It depends on the Lagrangian. But anyway, it's not canonical in the physics literature. So what we have to do is compute this symplectic, pre-symplectic might be degenerate, this pre-symplectic form. And the way to do that is just taking the pullback with respect to this. But the way is very easy because essentially when you're taking the variation, you just take the exterior derivative. And if remember here, we have this formula. So when you plug this formula in here, this theta will disappear and you will get only this. So that's what I have here. But now taking with respect to velocity, that means that this is 0 and you just get with this. So the momenta are actually going to be this. When you take the exterior derivative of this, you will get di. And then when you plug here, there is a lot of steps that I'm skipping, and I hope this might seem reasonable. That from here, you get the position here, and when you take the exterior derivative, you get here, and when you merge with that, you get here. So this is the induced pre-symplectic form from the canonical symplectic structure. So I hope with that, I presented what is called the covariant phase space, and I presented what is the or the canonical formalism. Now, how do we compare them? Well, when you have an action on the CPS and the covariant phase space is something like this, and we know that when you take the exterior derivative, you get something like this. However, in the canonical formalism, we get that this is the integral over sigma and the integral over dt, and when you take the exterior derivative of this L, you get this. So we have to break this L. That's as simple as that. Break the L into a tangential part and a normal part. Because it's a top form, it actually only has a tangential part. It cannot have a normal part. So you only have this. And this is the partial t is just like, because you're breaking into sigma times r, you have a t coordinate, and then you can take the partial t. So you do that, you compute this dl using this L, and you get something, you get a theta, this theta, after a lot of computations, a lot of, you have to do some assumptions that are reasonable, like kind of, yeah, they're very, very reasonable. So nothing crazy. You get this thing here. Now I put a little hat here and a little hat here because they live in different spaces. This lives in sigma, everything of this lives in sigma, and this will live on M. So there is a lift at some point that you have to be careful with that, because when you lift things, there are some ambiguities. However, these ambiguities will be included in here that I put here. So you can write them explicitly, but it doesn't matter. It's just some ambiguities that if you do the computation and I do the computations, we will get the same answer, except here, this dot, dot, dot will be different. Okay? And this dz, the same. It will be up to some z. However, when we compute the pre-symplectic form, remember in the CPS, we take the exterior derivative of that. And when we go to the space of solutions, the J is going to the space of solutions, then it does not depend on the Cauchy embedding. So in particular, we can take the Cauchy embedding T equals constant. And when you do T equals constant, these disappear. So the ambiguities that we had can be actually be removed, and we just get this. But however, this is actually the same as the canonical one. Okay? This is the last result that we got a few weeks ago that I put it on archive. Of course, there's a lot of details that I missed. And it's actually true for higher order theories, which is a bit tricky because the momenta are defined differently, blah, blah, blah. But still, this is true. And what I'm gonna, and this is actually true also for boundaries. But for that, I have to tell you how to add all the boundaries. And this is actually, I don't know, that's the part that I think it's very cool. I like it very much when we got that. So when you get, assume that you have M with some boundary M, and you just take a piece of the boundary that is of the same dimension, okay? So imagine that if you have a cylinder, for instance, the cylinder has the boundary that is like the lateral boundary, like a solid cylinder. The boundary would be the side, and then you will have the leads on the top and the bottom. So for instance, this N could be only the sides or could be only the leads, okay? It's kind of that, or a strip or something like that. And then this is the only place, and maybe someone here can tell me differently, but the only place that I've seen this definition is in the book of what is called Differential Forms in Algebraic Topology by Body2, where they define this object and they define this exterior derivative. And when I saw that, I was studying, like my brain had like this, like this light bulb turning on. And I said, this is exactly what I needed. This is exactly what I needed to make all these things work. And I was looking for more people doing this, because from here you get this, and you can prove that d squared is equal to 0. So you can do cohomology. And this is actually what is called relative cohomology. Most likely you have heard about relative cohomology, but in a different setting. The different setting is like you assume that they are forms over M, that they vanish over N. That's the usual definition. And then the exterior derivative is the normal one, because if something is 0 over N, its exterior derivative is going to be 0. So this is preserved, and you can do what is called relative cohomology. This is absolutely completely equivalent, but notice that this is more restricted, because you have to have this codimension 1. N has to be of codimension 1. Meanwhile, the relative cohomology, it can be any codimension. But when the codimension is 1, this is actually the same. So I was very excited. I tried to look everywhere, and I couldn't find absolutely anyone doing this. So I had to do it myself. It was very easy. I mean, if no one has done it, it's because no one thought about it. Because I'm not saying that, oh, I had this very fantastic idea. It's just doing some computations. And when you do that, what you realize is that the wedge, because you have to define what is a wedge, which Body2 is weird, because Body2 didn't They didn't do it. But you need it. You need an algebra. You need to tell me what it is. But the one that works is this one. So in the first factor, you always have to have the normal wedge, because this is the normal exterior derivative and the normal. I'm gonna explain later why it's this weird definition. And then in the boundary, you get this kind of thing. It's not important what is the particular one, but it's the one that makes that the Leibniz rule is satisfied between these two. And now what I also did is like, well, you have to define the integral of top forms. The top forms are going to be the n-dimensional, that are going to be top forms in M and top forms in N. So it's just the integral of M and the integral of N. And this minus, it's necessary because you put this minus. I'm sure that you can change a lot of signs, just choices. So now what I'm going to do is I'm going to integrate the top form, but an exact top form. These are called relative forms. So I'm going to take a relative form. I'm going to take its exterior relative derivative, it's called relative exterior derivative, and I'm going to take the relative integral. So when you do that, you just plug this into this. So you get these two bunches. And of course, now you can see, if you take the d alpha here, you use the Stokes theorem, but now we have boundary. So this goes to the boundary. So you get partial M, but this is only a piece of the boundary. So what you get is the integral over the pullback, but in the complementary of N. Okay, so this one gives you this, and you're subtracting this, so you subtract the domain. And now this d beta, you use Stokes theorem, and it goes from N to the boundary of N. Now you have to, the pullback is from the restriction, and there is a minus here because there is some change in the orientations, because you have to think that there are three manifolds. You have like M, the boundary of M, and the boundary of N. So there is, you can go through two different ways kind of thing to the boundary. So there is a minus sign. But once you have that, we can use just this definition and you get this. But now this thing, let's just call it the relative boundary. So if we call this the relative boundary, which makes a lot of sense, because if you notice, this is like the dual of this, d alpha delta n, and this minus this is this minus this. They are actually dual, which is the boundary is the dual of the exterior derivative. So this part can be just defined like this. And now if we define the pullback of the relative pullback, that if you notice, well, I didn't say, but I put an underline everywhere except the integral. I put it at the beginning, but it was very weird. So I remove it because it's already written here, but you might think that you put underlines everywhere. So these pullback, these two pullbacks, they are actually just the relative pullback. So if you notice, we have this equal this. So what is this? The Stokes theorem. Is the relative version of the Stokes theorem. I've never seen that before. Obviously, like, everything that I explained is what I did. Like, I didn't do anything else. So the whole thing fits in a slide. So I'm not claiming that no one has done it before, but I didn't see it. I didn't see it before. So you get the relative Stokes theorem. And then just for completion, I also deduce what is the interior product has to be. There is a minus, and the lead derivative is just by components. Of course, these are choices. I could have put a minus here and then a plus here or whatever, but this is the one that for me made most sense. So what I did is just I just created the relative differential geometry. Well, I mentioned that before. Quickly, but d squared is equal to 0, so you get homology, the relative homology, and of course the boundary is also the square is equal to 0, so you get homology, what is called the relative homology, and you get the Stokes theorem, so everything is the same. Now, once you have that, you have the exterior derivative, you have the relative exterior derivative, you have the relative boundary, and you have the relative Stokes theorem. You can see that the manifold Mn actually behaves as a manifold with boundary, given by this. So if you forget that this is a pair, if you call this M tilde, and you call this alpha tilde, and you call this the boundary of M tilde, and you call this the pullback of alpha tilde, you have absolutely, formally, it's exactly the same. You don't care if they are pairs or not. Formally, they behave the same. And not only that, if you take M and partial M, this behaves like a manifold without boundary. So because if you plug here partial m and n is partial m minus partial m is 0, or the empty set, and the partial, the boundary of the boundary is 0, or is empty. You get that this has no boundary. So for cohomological purposes, a manifold with boundary behaves like a manifold without boundary in the relative version. That's let's think it. Again, this is a very important thing. A manifold with boundary behaves like a manifold, like a relative manifold without boundary. But once we have that, we are done. We know how to solve the problem of the boundary. Well, we have to go to the relative bicomplex framework, which is just when you get the relative manifold times f, it's just the first times f and the second times f. And we can create the covariant phase space formalism with boundary. So remember, we have an action that depends on one Lagrangian, but now every time that we see a form, we put a pair. Every time we see an operator, we put an underline, and we're done. We are absolutely done. Everything that is cohomological, that's important, has a relative version. So here, we just put a pair here, a pair here, a pair here. Now, instead of one Lagrangian, we have a pair of Lagrangian that is a relative top form. So it belongs to this thing. This is an n form on n and a 0 form on f, and this would be an n minus 1. Oh, well, here I put n, but it's the boundary. So it's the boundary of m. The boundary of m times f. And we're done. Now, the theorem we had before is that the L prime is equal L plus something exact. They're equal on cohomology, then their actions are the same. The relative version is if they are equal on relative cohomology, so they are equal up to relative exact form, then they're equal. And that, I'm very amazed because if you read the physical literature, they will say very wrong things about, oh, you can change the Lagrangian by an exact form, and then things don't change, but then you can take a very nice representative, blah, 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 which is true when you don't have boundary, but they use it when you have boundary. And then you're changing the cohomological class because you have to change also the boundary. So this is the cohomology that you have to use, and they don't. Well, hopefully they will start. So the actions are the same. And the same is true for the opposite. The converse is like, remember, when you have two actions that they are equal over contractual boundary, they are equal on cohomology. Now is the same on relative cohomology. You have two actions, they are equal on relative cohomology because the Stokes theorem is the same, it's cohomological. Now the space of solution is defined in the same way as the singular point of this action. And then when you compute, before we computed this and we get this theorem, now we have to do in the relative form. So instead of the normal D, we take with the underline that I forgot to mention which one is it. This is everything that is double. The relative version is just component wise. It's the first component, the second component, because the fields don't care if you have boundary or not. They are just defined, and the things that you do on the fields is like in the vertical direction, and the boundary is in the horizontal direction. So they don't care. Everything is the same. However, this theorem that I put here, this is not cohomological. And that is very important because then the relative version might not be true. So when you plug this in here, you actually, what you get, you have to integrate by parts and you get an additional term. And this term might not be written like this. So here you have equations of motion side the variation by something exact, and you would hope that this is also true, but it's not always true. But this is where the physics come in. The thing, what I'm saying is like, usually you can put any Lagrangian on the ball, but on the boundary, you cannot put any Lagrangian. If you put a Lagrangian on the boundary that is weird, it will give you weird boundary conditions that might not be compatible, let's say. And one way to check, or this is a sufficient condition. What I'm gonna say is like a problem is well posed or physically well posed. Let's say if this object can be break like this. And when you do in practice, what you get is some normal derivatives of the variation. When you get normal derivatives of the variation, you cannot integrate by parts essentially. So things are wrong. So what you have to do is actually choose wisely your L so that this is true. Or you have to choose wisely your space of fields, because in the space of fields, you can put boundary conditions. So if you put boundary conditions such that this is true, or you pick an L such that this is true. But once this is true, we have actually this result. because remember, this can goes to the other side, and this is actually, let me show you before, this is here. This is gonna be this term. This is the theta that appears here. So we get this. The exterior derivative in the fields of the pair is gonna be something times the variations plus something that is exact. And when you plug this into here, the relative Stokes theorem tells you that this is 0, and then you only get this. So you get that the space of solutions is given by equations of motions and boundary conditions. But this is a very important thing. Everything that is cohomologically is true, automatically true, but this is the only one thing that is not homological in this whole scheme. So you have to impose it by hand. Great, once we have that, we remember that when we had a Cauchy embedding, we take the exterior derivative of the theta of the symplectic current and we integrate. So now we just have to double. Whenever we have one form, we take 2. Whenever we have an operator, we take the underline, here the underline, and here a pair. And we're done. So we know that this is the form that we have to have. The exterior derivative of the symplectic current on the bulk and the one on the band. And this is a term that everyone forgets. Or they put it by hand. They realize that, oh, something is wrong. So they choose a representative such that this term appears. That's how they were doing. So it was very, sometimes I try to sell this to physicists and sometimes like, yeah, but I know which term is it. I knew that. And they showed me like, yeah, I found it. I was like, yeah, but you do it by hand. You had to know the answer or you had to know something before getting the right one. Here is like, I don't care. You might choose a different one. Here, you might choose a different theta, but then the choice of theta will appear in here and then we'll change it, the theta prime, this the capital one and the small theta. So the different choices will appear here. You can do a different choice. I can do a different choice. We are gonna get the same. Why? Because if you take a different one, they're gonna be equal up to exact in the vertical direction and exact in the relative horizontal direction. And this is very important because it's in the relative. And once it's in the relative, when you take the by the Stokes theorem, because they commute or anti-commute, this is gonna be 0, d squared is also gonna be 0, so you get the same answer. So that is how you can include boundaries in a cohomological fashion. Of course, this is again, depends on the embedding, but if we go to the space of solution, it does not depend on the embeddings. And I think that's all I want to say, just to get some conclusions. We have developed a new formalism to derive the covariant phase space, symplectic form canonically associated with the action. That is very important because there were already procedures. And it's like, oh, you get this action, and then you get this, and then somehow you pick a representative such that at the boundary behaves like one. But that was not general because it depends on the action that you had. For general relativity was one, for electromagnetics was another one. So it was not a general formalism. So this is the first time that it has been developed. We have also proved that the covariant phase space and the Kant's symplectic structure are equivalent. And we did it with boundaries and for higher order theories, which these, by the way, proved that our construction here was the good one, because it's actually the one that comes from the canonical presymplectic form of the cotangent bundle. So that's another way to say, yeah, that's a good one. Well, the bicomplex formalism is essential, and we actually coined what is called, we call it the relative bicomplex formalism. That is this new formalism, we call it like that. So we actually merged two things that they were already done. That's what it takes. Just read a lot and link stuff. And this is also true for higher order theories. And we have successfully applied to several theories of gravity, solving some of the questions, because people were wondering when they were adding boundaries, things were wrong at some point, so they had to make choices and blah, blah, blah. Especially when you consider equivalent theories of gravity written differently. And it's like, but it's not matching. I was like, yeah, because you're taking different representatives in one theory and in the other. However, what we prove is that they are actually on the same relative cohomology class. And for them, they couldn't prove that because they were only considered the bulk. And in the bulk, even when they are in the same cohomology class, they are not in the same relative cohomology class. So that's all. This is our paper. about the geometric formulation of covariant phase space, and this is the last. We published in April. We are still in April, so yeah, so it's April, but it got accepted already, also in physical. So that's all. Thank you so much. If you have any question, please go ahead.
Thank you very much, Juan. All right, are there any questions?
Yes, sorry, Juan, I had a question.
I cannot hear anything. I don't know why.
Sorry, you cannot hear
no.
us.
What about now?
Ooh. Wait a second. I'm gonna. I think they are. It's a very weird. It's gonna remove my computer, and I'm gonna. I thought it was mute. Myself. Okay, let me try again. Can you talk?
Yeah.
Can you hear us now?
Yeah.
Good.
Okay. So I had a question, Juan, but just to know if I had understood well this, what you were explaining is, in the middle of the talk, you said that there's a problem with when you have a boundary, because in that integral, Stokes' law failed, and that term, it depended on the alternative form you chose. And then you fix, the way you fix this boundary, the existence of the boundary is not a problem anymore with the relative cohomology, if I understood well. No, the relative cohomology is the tool you have created,
Yes.
well, you have used to create a new procedure to also be capable of using this covariant procedure when you have boundary, no? And then the Stokes' law works because you have boundary, but the term is also zero in the Stokes' law. Is this more or less what you did? Okay.
Yes, it's exactly that. Yeah. The thing is, like, what I'm saying is, like, here, if you take a different z, it's gonna depend. And what I'm saying is, like, okay, you have to choose a theta, but you also have to choose a small theta. And this choice by pairs is the one that is independent. Because here, if you choose only a theta, what you're actually doing implicitly, although you don't know, is choosing theta comma 0. And then if I choose a theta comma small theta, they might not be in the same cohomological class.
Okay.
That's what I'm saying. That's what I'm saying. If there is boundary here and you don't choose a theta, a small theta, is because you're choosing it 0. And the thing is, like, if you choose a big theta and a 0, and I choose a small theta, a different theta, and then 0, then they are not in the same cohomological class. If I choose a different big theta, I have to choose a different small theta so that they compensate and they are in the same cohomological class. So that's the problem. Like, if you choose big zeta, comma 0, and I choose zeta prime, big zeta prime, and then comma 0, they are not in the same relative cohomology class in general. However,
Okay,
if you choose...
Sorry.
Huh?
Yeah. And the composition that relates the big theta with the small theta, that was in one of the last slides. Is this unique?
It's the... so it's actually given by this. So the maybe I didn't put it.
This
one.
Okay.
It's this one. So this theta prime, is just because it's the same decomposition. And this term doesn't pose any problem, but this one poses, because this one, this DC, this big C, there is the pullback of the C. Remember the exterior derivative, where it is. No, sorry. Where is the exterior derivative? Here. When you take the Z, this is dz, and then the pullback of the C in here. So this term is the one that causes all the problem. And that comes from the Stokes theorem. So if you don't take the relative form, this is not true. If you just take by pairs, let's say you apply the D in here and the D in here, this is not true. Because you integrate, when you integrate, this one will go away, but this one will give you a boundary term. So that's why you need the relative form. So two choices, theta prime and theta big theta and small theta, they're going to be equal up to relative exact form. If you don't take the relative and you just think, oh, I'm going to work by like component wise, this is the exterior derivative of the first one and the exterior derivative of the second one, there is a boundary term that appears. And then cohomologically, they're not the same. They're not in the same cohomology class because in particular, the integral is not the same. So if the integral is not the same, they are different. Because the integral cannot depend on the cohomology.
Okay.
So the problem is like most people would think, or either they completely forget about the boundary, so they don't care about the boundary, weirdly, or they do, but then they think that this is component-wise kind of thing.
Okay, thank you.
More questions? All right. If not, we can thank our speaker again. This time, maybe hearing us.
Thank you so much. That was very nice.
Thank you very much, Juan.